All right, good afternoon. Let's start lecture. Okay, so in the previous lecture we have looked at the stiffness of a bolt, stiffness of the member. Okay, the stiffness of the member. There's the equation in basically for different frustums, and I'll go back to this member stiffness again once we finish this portion right here. Okay, yeah. Anyway, maybe just a quick review at here for what we did in the previous lecture. Okay. So especially the member stiffness. As I mentioned, there will be a question for this in the final exam for sure. Okay. So member stiffness basically refers to how do we calculate the stiffness of the members that are being clamped between the bolt head and also the nut. Okay. The essential formula what we do is we use a so-called symmetric pressure cone to model the distribution of the pressure, and then we will look at the stiffness of many frustums, okay, and each frustum will be modeled using a trapezoid, and the formula for the stiffness of one frustum is given over here, and the alpha value 30 degree, so basically which is this formula. So that is the formula for calculating the stiffness of one frustum. Okay, and the frustum always takes a trapezoidal shape with certain thickness and certain width, capital D, at the top. So if you have a specific case like this, okay, make sure that the top and the bottom, okay, the width are always just 1.5 times the D, and D is the major diameter of the bolt. Okay, so given a specific question, it really depends on the member thickness and also how the members are being clamped. There might be a washer on the top, so the washer will be also part of the member. Okay. And also depends on the material of the member, so it could be steel, cast iron, or it could be all the same steel. So you're going to have to appropriately divide these members into different sections or different frustum right here. Okay, yeah. So once you put them into appropriate frustum, and basically there are many layers of trapezoid. Then each layer of the trapezoid, the frustum, the stiffness of that layer should be calculated using this formula right here. Okay. So for this one here, there are only two members. One is steel, one is cast iron. Suppose the steel thickness, the member is a little bit thinner than the cast iron. So the conical pressure distribution will be drawn or sketched something like this. So in this case we have 1, 2, 3 different frustums. Okay, 3 different frustums in here. Then I will calculate stiffness 3 times according to each one of the frustum. Right. So first frustum starting from the beginning. So the capital D is 1.5 D. Okay, and the thickness is basically the thickness L1. Okay, that's easy. The second frustum, which is this, so the capital D is the width of the bottom of the previous frustum. So we need to calculate the bottom width of the previous frustum. So you can calculate, okay, using simple geometry. So that's basically twice on the side plus what's in the middle. Okay, so that's how you calculate this capital D. Okay, and once you get this, you can calculate thickness based on the actual dimension. Plug in the same formula, and you get the second member stiffness. And the last stiffness, which is the bottom right here, so that covers the whole trapezoid. So even though this is upside down, so your capital D is the short side of this frustum. So don't use this side here, right? Use this side. So that's still 1.5 D, and then you can calculate K3. And once you get all these 3 stiffness, so your total stiffness is 1 over K1, 1 over K2, and then plus 1 over K3. Right. So that's how you can calculate the stiffness for members here. Okay. Now Once we solve these two problems here, so we're going to have to look at the next topic, which is basically the tension joint safety analysis at here. Okay, so we'll combine basically this portion. Once we finish this, we'll combine everything together, so we'll be able to analyze the safety of a bolted joint, okay, and tension joint particularly. Okay, so first of all, let's look at basically a couple concepts at here. Okay, so first concept is called the bolt strength. So bolt strength, underneath this one here, there's an important concept called proof load. Okay, proof load, FP. Okay, proof load, FP. FP, the definition of proof load is basically it's the maximum load, okay, before permanent set. Okay, before permanent set. So I can illustrate this using the stress strain curve. Okay. If this is the stress and if this is the strain and here. So the typical curve, initially it's basically straight line, right? Straight line. And then up somewhere the straight line started to tilt now. So basically, right, it started to flatten, tilt. Okay. So this basically this point at here. Okay, so this point at here is the so-called, okay, SP. Okay, so what SP basically means is so-called the proof strength. Okay, proof strength. So SP and FP are related together at here. So your SP is equal to your FP divided by the tensile stress area for the bolt. Okay, so you have a bolt, you can calculate the tensile stress area, or you can find it from the table. Then the force divided by the tensile stress area is the proof strength, and that's the proof strength over here. You know, a little bit further from that, and then you don't have the linear deformation anymore. Okay, yeah, and that typically corresponding to 0.1% of permanent set. Okay. So of course, as you probably know, a little bit further you get your SY, right, your yield strength, but that's not the concern here. It's the SP here. Okay. Now to find SP, you actually have table 8-9, 8-10, and 8-11 to make use of to find this proof strength SP. Okay, so I'll show you what these three tables look like. And this is the three tables we're talking about here. Okay, so I don't quite remember which one is which, but there are three tables. This one here is the ASTM specification. As you can see, this column here called minimum proof strength. So this column here will give you the proof strength SP value for different basically designations at here. Okay, yeah, and it's actually quite interesting. You could also tell basically the strengths or proof strengths of the bolts by looking at the marking, the so-called grid marking on the head, the bolt head. So there are different ways of labeling the marking, and also possibly they actually stamp the grid number, okay, designation number on the top of the head. Same thing for SE the specification. So that's SE grid number, and this is the proof strength corresponding to that SE grid number. There's also markings on the bolt head. Okay, yeah. One of the capstone group I'm supervising right now, actually part of their job is to find a specific bolt. Yes. Is this, well, that doesn't work. So is this still working? This okay? A little better, right? Okay. So just make sure you know what table to make use of to find the proof strings. Okay. The question maybe will give you is, okay, so you're using, for example, you're using metric type of bots of grade 5.8. So that's where you can look at, okay, 5.8. This is the range of the basically the major diameters that can be 5.8 grade. Then the proof of string set here is 380 megapop basically. Okay, so that's when you can make use of the tables here, the 3 tables. Okay. So these 3 tables, they are all in the textbook, by the way. Okay, yeah. The values set here. Another thing I think I pointed out a long time ago. The values here, why they call it minimum, right? So minimum proof strings basically is minimum. It means if they manufacture a batch of the bots, okay, and they do a testing, if this is the distribution of the test results, then the value they're giving to the customer is actually the minimum value at here. So that's why in the table it's called the minimum value. Okay, and then actually in many of our appendices, they're all called the minimum value essentially. Okay. Yeah. Okay, so the 3 tables corresponding to 3 different type of sort of a grading standard. Okay, and just read the question carefully and use the corresponding table appropriately. Okay. Another concept here is called the preload. Fi. Okay, it's the preload. Okay. What preload basically means is, you know, when you have a nut, when you have a bolt, and then you plug the bolt through the member, and then you crank the nut on the other side, right? So how much torque you apply, how tight you crank the nut, okay, that basically will act as this so-called preload at here, Fi. Okay, yeah. So as you can imagine, right? As you can imagine, essentially, when you tighten up the nut, what type of stress does the bolt feel? Tension, right? And what type of stress does the member feel? Compression. Okay, yeah. So the amount of cranking or tightening, right, give you this preload or give you the pre-stress applied to the nut and also to the member here. Okay, yeah. It's a very important. The preload concept is actually quite important because if you are using the nut for a tension joint, like a pressure vessel, okay, the amount of the preload ultimately determines the safety of that joint. So it has to be applied appropriately, okay, and otherwise it'll affect your safety of the joints here. Okay, yeah. So properly, the definition is basically the tensile load, okay, that stretches the bolt, okay, by tightening the nut. Okay, so that's the preload concept here. So I'll show you a picture to kind of illustrate why the preload is important. Okay, let me find the picture here. Okay, so this is the picture I want to show you. Okay, yeah. Okay, so take a look at the picture. So this is sort of illustration of the preloading of a bolt set here. Let's say, for example, right? So in this example, what we do is we consider the bolt as if it's a spring. Okay, consider it as a spring here. So if it's a spring, then we can pull the bolt down, right? Put it down here. So like you're pulling the string down, right? Okay, and then after you put it down a certain amount of the distance, then we insert a stop here. Okay, you know, stop. So that basically that spring, essentially the spring is like either compressed or stretched. There's a certain amount of a spring force, right, reserved inside the spring here. That makes sense, right? So now you have the stop here, everything's stationary, right? Stationary. So if from this stage, if you're trying to pull this nut, or if like basically if this is application of pressure vessel, if some sort of internal force trying to push it outwards, right? Yeah. If this force, if initially you put a 100-pound of force at here, then any external force that is less than the 100-pound force, then that stop will not fall out, right? The stop will not fall out. And you can consider this stop as if the joint, okay, as a joint here. But if this any force that's greater than the 100-pound force, then you can elongate more, then that stop will fall out. It's like the joint basically failed. That makes sense, right? So that's why the preload at here actually determined how safe, or basically determined when the stop will fall off at the joint here. Okay? So apply appropriate preload is important, especially for our application at here. So how do I apply the preload then? Here's a guideline here. Okay? We have two different type of joints. If it's a non-permanent joint, okay, so we can apply our preload as 0.75 times the FP. Remember what FP is? It's the proof load, right? It's the load corresponding to the proof strength. Now, if you have it's a permanent joint, then you can use 0.9 times FP. Okay, so that's permanent joint. Permanent joint, non-permanent joint, the difference basically is if you have a certain, let's say, maintenance requirement that needs to be done regularly, then that joint needs to be a non-permanent joint, right? If somehow you don't really require any maintenance in the next 10 years, okay, or you just want to use it until it's the end of the life, then you use the permanent joint essentially. Okay, yeah. So this is the guideline for applying the proof load at here. But of course, the point at here essentially, how do I know that I have appropriate preload applied at here, right? Yeah. So now this is basically kind of topic at here. How do I relate, okay, the preload, okay, to the tightening torque, okay, to the tightening torque, because you're torquing the nut to apply the preload, right? So how do I know, basically how much of preload has been appropriately applied here? So there are a number of ways or number of methods here that you can make use of to achieve appropriate preload here. Okay. So the first method is a very mathematical method here. Okay. The first method here is we do know when you apply certain load, then you're elongating the bolt, right? Because of tension force. And the delta change between the length and the preload is related with this formula. Okay, so it's basically the stiffness formula, right? So you have this amount of change due to that amount of Fi at here, right? So then I can inverse calculate. So okay, so I don't really actually so let's say if I give you Fi, right, from the calculation at here. So let's say I use this one here. Okay, so if I calculate Fi based on a certain proof load Fp, then I can plug in over here. Then we'll be able to get a delta equal to some sort of a value at here, right? So which basically means you need to crank the nut and elongate the bolt by this much of a small offset. Does that make sense? Right? Yeah. But immediately you can probably say, oh my god, so I need a really accurate measurement here, right? For this delta here. Okay? Yeah. So that it's very mathematical, but not very practical, right? Very practical. Okay. Yeah. So there are a few other options we can do. Okay. There's another one here called. Okay. Basically, this is just using the torque wrench. Okay. So torque wrench, it's an equipment. It's a tool that can give you the amount of torque that or you set the amount of torque that you want to apply, right, to the nut. Okay. So here, how much torque should we apply then? We have a formula inside our textbook at here, basically in terms of the formula for the T at here. So this formula comes from a formula that we actually derived in previous lecture, which is this right here. So this is the formula we derived from previous lecture, if you recall that. And that's the formula that we used for the amount of torque that you need to apply to raise the load when you're using a power screw, right? Yeah. And this formula can be simplified, okay, into a format like this. So K times Fi and then times the major diameter D. Okay. Now the K at here, this is from a table 8-15. Okay. This is the parameter that depends on the surface condition. Okay, surface condition with the bolt and the nut. So I'll show you what this table 8-15 is. So this is the table 8-15. Here lists the bolt condition: non-plated, zinc plated, lubricated, cadmium plated, right? And then you choose your K from the second column right here. Okay. So then you plug it into here. So you get certain amount of the torque that you need corresponding to that certain amount of preload. Okay. So that's how you can set your torque range in order to apply appropriate preload here. Okay. So that's another approach here. Okay, that's another approach, and there's a few more approaches here I want to show you using the PowerPoint here. Okay. Okay. So this is another one here. Okay, it's called the turn of the nut method. Turn of the nut. So this is when you don't really have any tools and you wanted to approximately apply the right amount of preload. So the approach is, first you reach the so-called snug tight condition. Okay, snug tight basically means the tightness attained by a few impacts of impact range or the full effort of a person using the ordinary range. When snug tight condition is attained, all the additional turning develops useful tension in the bolt. Okay? So if you have a heavy hexagon structural bolt, then the nut should be turned a minimum of 180 degrees from the snug tight condition. Okay? So that's basically when you don't really have any tools, you can use this type of simple approach here. Nowadays, there are a few more basically type of technology you can rely on to give you peace of mind. So this one here is called a torque limited fastener. So as you can see in this fastener here, at the end of the fastener here, there is a spline extension of the end here for the bolt on the bolts at here. So the tools basically, if you apply the amount of the torque appropriately, and then the ending will be twisted off. Okay, so if the ending is twisted off, then basically it's indication that you are at the right amount of torque or you are at the right amount of preload at here. Okay, so that's one unique way of telling people when to stop. And this one here is using the so-called load indicating washer. So this type of washer is called the bell-well spring washer. The bell-well spring washer is used sometimes under the bolt head, but mostly basically between the member and the nut. Okay, yeah, and it's designed to basically give the desired bolt force when basically the top notches are being fully compressed flat. Then that's an indication that that the right torque or amount of preload have been achieved. Okay, yeah. And the last one here, this is actually kind of neat. It's called self-indicating direct tension indicator. So DTI in here. So I'll show you. There's a little bit of animation in here. So there's some materials inside these bumps at here. So they are usually a flexible silicone embedded in the depression under the bump. So if you crank it and with a certain amount of torque, and then the material will be squirting out, and that basically is the indication that you need to stop tightening. That's all that it is. Okay, yeah. So this is actually more expensive, of course, yeah, but I can imagine it's a little more accurate. Okay. Sometimes whenever you finish this, rerun this one. Okay, all right. So that is the torque part. Okay, the preload. Okay. So now let's take a look at the tension joint loading. Okay. Yeah. Let's look at the tension joint loading, the actual loading, what happens at here. Okay. So I'm going to copy a figure into my, copy this figure right here. Okay, so this illustration is essentially just a typical illustration of, let's say, tension joint. You have a certain amount of members between the bolts at here, right? In this case, there are two washers and two members at here. Okay. So, and you have certain external loads, and it could be the external load from the pressure vessel. So the P here is the external load. And of course, you tighten the nuts and apply preload to the system Fi. Right? So that's the loading condition at this one location bolt. You may have multiple bolts at for the application, but this is just one bolt location here, right? So I'm going to define myself a few notations at here, okay, for the next derivations. Okay. All right. So capital P, as I said, okay, that refer to the external tensile load. Okay. So external tensile load, and Fi, okay, is the applied preload. So once you have this situation in here, so you can imagine basically if there's no preload, if there's no external load capital P, then what happens is the bolt will feel this Fi, which is a tensile force, and the member will also feel this Fi, which is a compression force, right? Okay. Now, when the external load comes into the picture here, so the external load basically trying to push the two members away from each other, right? Yeah. Then part of this external load P will be basically felt by the bolt, and a part of that will be shared by the member at here. Okay? Yeah. So I will separate this P, okay, into two portions. And at the PB, I call it the portion of P, okay, taken by bolt. And then PM, I'll call it the portion of P taken by the member. Okay. Yeah. So part of the P goes to the member, part of the P goes to the bolt, right? Yeah. So now, once the existence of P shows up, so now you can imagine the force on the bolt is not going to be just Fi anymore, right? So we'll basically have a new force on the bolt. We're going to call the Fb, which is basically what we call the resultant bolt load. Okay, resultant bolt load. So you can see the notation-wise, resultant bolt load means Fb equal to Fi plus the Pb at here. Okay, so Fi plus Pb. So more tension, right? More tension force on the bolt. Okay. Similarly for the member, right? So let's define Fm. Okay, so define Fm right here. So this is called the resultant member load. Okay, resultant member load. So resultant member load, what would that equal to then, right? See, initially how much load on the member? Fi, okay, which is compressive force. So it's negative Fi at here. And now the amount of external P and the Pm, which is the portion of the P taken by the member, and that actually acts as what? Tension force, right? So it needs to be subtracted out of this Fi. So basically negative Fi plus the Pb, not Pb, Pm, okay? And that's give you the amount of Fm at here. Okay? Yeah. So as you can imagine, for this calculation, what do you think the sign of the Fm is? What do you think the sign for the Fm? Negative, right? And what happens when it's positive? It's failure, exactly, right? So if it's positive, meaning there's no compression force on the member anymore, basically means you can imagine the two members do what? Separated, right? Yeah. And that's exactly something that we will actually have to prevent it from happening, okay? Part of this member here, part of the joints here. Yeah. So technically speaking, we want, right, Fm to be less than 0, okay? Yeah. So, and now let's do a little bit illustration at here. So what's really happening at here when you have this kind of transitional forces at here, right? So I'm gonna illustrate, okay, using a typical, basically like a load and a deflection, that type of tire diagram here. So if this is the load at here, and this is the deflection delta, let's call it deflection delta at here. So this is the process, right? If you initially apply the Fi only, right? If initially Fi only, so then we have on this side here for the bolt, okay? So the bolt here, so it'll go up, okay? Well, this is Fi, and this is basically, let's say, the deflection corresponding to the Fi at here. Okay, does that make sense? Right. So if this is the bolt here, you apply Fi, it'll be deflected by a delta B. Now if you have the member over here, then you apply the Fi, okay? So if this is Fi, of course this is negative Fi here, and that's the amount of compression, right? That's the amount of compression on the member. So the member felt is a compressive force. Okay, good. So now the external force coming to the picture now. So external force P come to the picture. And then you have a part of Pb goes to the bolt, and a part of Pm goes to the member here, right? So Pb is the additional force okay, applied to the bolt. So that basically you have amount of additional force at here. So this is FB equal to FI plus PB. Okay, and that additional force will cause an additional amount of a deflection at here. Okay, so this will cause additional amount of friction. So how much additional flexion is caused here? So this portion, let's call it delta, and that's due to the PB, and divided by the stiffness of the bolt, then you get the additional deflection. Okay. So on the other side, the member side here, the member has a PM coming into the force, the components there. So, but PM is a positive number. So basically, instead of Fi here, so then after the external force, where are we now? So we're somewhere here, and this is your negative Fi plus the PM over here, right? Negative Fi plus PM. And then the corresponding location of deflection is this location now. Okay, this location. Now, because everything moved, okay, everything moves from an original equilibrium condition, right, to the current equilibrium. So basically means the amount of deflection reduction at here compared to the amount of reflection increase at here, they should be the same. So that's also delta, but in terms of the calculation, you can use the PM over the Km to calculate, but they should give you the same amount of deflection delta at here. Okay? Yeah. This is basically inherently what's happening at this loaded joint at here. So now I'm gonna just try to update the formulas here a little bit based on the diagrams over here. Okay, yeah. As we can just see, basically we have just seen is your PB over KB is equal to PM over the Km, and that give me the PM equal to PB times Km over the KB at here. Right, I give you this relationship. At the same time, just bear in mind, you also have the original relationship. So PM plus PB is the total external force, capital P, right? Total external force, capital P. Okay, so now I'm going to define basically a so-called constant at here. It's called a fraction of external load constant. So define capital C at here. Define the C as PB over PB plus PM. Okay, so we're going to define the C as PB over, or just basically PB over capital P. Okay. And and based on the relationship that we have derived, based on this relationship at here, okay, based on this relationship, your C at here can be also written as KB over KB plus Km. Okay, so that's your C value. Okay. So instead of relate to the portion of the load, okay, from the external force, it's much easier to do this. So your KB, Km, so the stiffness of the bolt, stiffness of the member, which is exactly what we just did in the previous lectures, right? Yeah. Okay, that's your C at here. Okay. Now with this C value here, then my original, these two equations, okay, so these two equations at here, I can rewrite them, okay, using the newly defined constant C. Okay. So as you can see, basically FB, you can see FB equal to what? FB equal to originally is PB plus FI, right? Yeah. PB equal to FI. And PB is C times capital P, then plus FI. Okay? Plus FI. Right? So this formula FB can be written as C times P plus Fi now. And then that Fm, the resultant load on the member. Okay. And this one is negative Fi plus Pm. Okay. So this will become 1 minus C times P and then minus Fi. So C essentially it's a portion. You can see the definition of C is the portion of the external load, right, applied to the bolt, and 1 minus C is the portion of the load applied to the member. Okay. So these are the two formulas, one for FB and one for the Fm. And I was just actually just looking at the Fm here. As we see, right, Fm, okay, needs to be less than 0. Okay. If somehow Fm turn out to be greater than 0 now, then you essentially have a separation of the joints. Okay. Alright, so that's the internally how the load is being going up here. So here's one simple example here, okay? And before we move on to the actual analysis of the joints. Now, typically, your member stiffness, okay, is about 5 to 8 times, okay, bigger than the bolt stiffness. Okay. So if I plug in that range into the formula for the C, and I would get a range of the C is probably around 0.11 to 0.16. Okay. So that's just empirical values here. Okay. So let me show you an example here to get some more intuitive understanding in here. Okay? Let's see, in this example, I'm going to assume Km equal to 8 kb. So the stiffness of the member is 8 times bigger than the bolt stiffness. And we have a preload of 1,000 pound force, and external load P equal to 1,100 pound force. Okay. So let's take a look at given the current situation, right? What's going to happen here? Okay. So first of all, we can calculate the C value, okay, based on the given ratios between member and bolt stiffness. So C value is Kb over Kb plus Km. Okay. So you can plug in Km equal to 8 at here. You get 1 over 9. Okay. So that's your C value. Okay. Then the amount of a force, okay, external force taken by the bolt is C times P, so it's 1 over 9 times 1,100, and which is 122 pound force. Okay, so that's how much force being taken by the bolt, right? Yeah. And then you can calculate the amount of force taken by the member, okay, or which is just P minus PB. So that gives you what? 970 pound force. Okay. roughly. It really doesn't add up here, right? So this add up. If I wanted to add it up, what should I get? 8? Yeah, that add up. Okay. So from here you can actually immediately see the majority of the external force are being taken by what? By the member, right? Yeah, by the member right here. Okay. Yeah. So with this distribution, then I can calculate the FB and FM value. So FB is PB plus FI, which is 1122 pound force. FM is 1 minus C times P, and then minus Fi, which is negative 22.1 pound force. Okay, that's the result set here. Okay, that's the result. So you can see the joint here is still safe because this is still less than 0, but it's quite close to 0 now, right? Yeah. So that's fine here. But so you give you a sense of basically how the load are being distributed between the member and the stiffness set here. Okay. Now, what would be the factor actually? Let's say if you want to change the distribution of a load, right, to the member or to the bolt, so what kind of parameter that we can adjust or manipulate to make some effect there, right? So one of the things basically you gotta basically just a comment set it here. Okay, so just comments. Let's say we need to look at essentially from the formula C at here. Okay, so PB over P, that's the C. So the value of the C basically determines how much portion of the external load going to go to the bolt, how much go to the member, right? And this one here, as I said, you could rewriting as the parameter for the member stiffness, so KB over KB plus KM. Okay. So you can see the KB is this and the KB at here. So now if you remember in the previous lecture, I can rewrite it again here. This is 1 plus KM over, let's say, KB at here. Okay. That's another rewriting at here. So let's look at this question. This expression at here. KB is the bolt stiffness. Okay, it's bolt stiffness, and the bolt stiffness formula from previous lecture is what? Is this ADAT times E and divided by AD times LT and then plus AT times LD. Okay. And if you recall that, this is essentially one of the very important table that I mentioned in the previous class is table 8-7. Okay. And that's part of the exam questions. Okay. So ADAT are the area, AT is the tensile stress area, and AD is the major diameter area. E is the Young's modular, and LT is the length of the threaded portion within the member. LD is the length of the unthreaded portion within that clamped member. Okay. So bottom line is the length. If you can modify the length LD LT, right? And guess what? You'll be able to modify the KB value, and then the change of KB value will change the C value, and then that'll basically resulting in the portion of the load change, right? Okay. Yeah. So there's another important parameter called the grip. So grip is basically LT plus LD. So the portion of unthreaded plus the portion of the threaded, okay, within the members, within the clamps, bolts, and the head. Okay, so then this is the grip here, right? It's the grip. Okay. So now you can see now I can make a conclusion. I can say essentially the longer grip, okay, so the longer grip, okay, if I have a longer grip, meaning what? Meaning somehow the LD and the LT is part of that is longer, okay. So if I have a longer grip, essentially means LD or LT will be bigger, right? Then translate to the stiffness calculation, meaning the KB will be small? Yeah, will be smaller, right? If KB is smaller, then going back to the C formula at here, meaning this is going to be bigger, so the C will be bigger, right? C will be bigger, okay? Yeah. Now, hang on a second here. Smaller KB means bigger value for this term. Then overall the C should go what? Should go down, right? Should be smaller. Okay? Should be smaller. So the conclusion essentially, if you have a longer grip, then you would have a smaller C value. Smaller C value basically means what? The amount of a load shared or taken by the bolts will actually be smaller now, right? So the more load go to the member, right? Yeah. So that's sort of when you design for tension joint, right? You can kind of imagine, how you want to manipulate the C value at here through the grip lengths, okay, to reach. If you want your bolt to share more load, then you definitely don't want longer grip. Okay, you want a smaller length of grip. Okay, so that's the part of the loading at here. Okay, so now let's look at the safety analysis at here. Okay. Let's look at the safety analysis of tension joint. And the focus we're going to have here is we're going to focus on the static load. Okay, I do have fatigue load in the lecture, but we'll make it an optional, so we're not going to test you in the final. So, but the static load will be part of the examination. Okay. So first of all, there are three different ways of analyzing the safety of the tension joint at here. Okay. And I'll show you the first one first, okay, and then basically different cases. First of all, let's look at the tensile. Let's look at the tensile stress on the bolt. Okay, so how much tensile stress the bolt felt? The tensile stress. Let's use the sigma b for the tensile stress at here. Very simple. So static one. We use the resultant load on the bolt divided by the tensile stress area AT, right? So you got basically the tensile stress. And FB is CP plus FI and divided by AT. Okay. So that's tensile stress. Once we have the stress now, then we basically have three different types here. Two types directly related to this one here. So the type 1 analysis is this. So type 1 here, all you do is you calculate safety factor, okay, by comparing your proof strength and the tensile stress. So proof strength is basically the limit, right? It's the limit for the bolt, and you compare that with the tensile stress at here. So you get SP times AT divided by CP plus FI. That's essentially one type 1 analysis, and this one here you can call it a yield. This is like basically like a yielding at here, okay? Like a yield factor, safety factor. Okay, yeah, that's the first one. The second type of a calculation, okay, it basically, instead of getting a safety yield, safety factor here, so what we do is we apply a factor in front of this load, external load, capital P. So you can basically say, okay, let's put a factor NL in front of the capital P at here, and then plus Fi. Now this time, when I divide it by AT, I'll let it equal to basically the proof strength SP. So from here, you can solve for this NL, okay, which is basically what we call the load factor at here. So NL can be solved, which is SP times AT minus Fi, okay, divided by Cp. And this is called load factor. Okay, load factor. So it kind of makes sense. Essentially, you're like putting a weighting factor in front of the external load, right? And you don't want essentially too much of external load being applied to cause the unsafe situation. Okay? Yeah. So that's the second type of safety factor. Okay, so you can see they're not the same. The type 3. Okay, the type 3 safety factor here is it's directly related to the condition of joint separation. Okay, so joint separation, we call it joint separation factor. Okay. So in this case here, what you do is you want to make sure that this Fn is less than 0. But you look at, of course, the extreme situation. So what happens when Fm is 0, right? Is the member resulting force is 0. So all you need to do is, so here is the formula for calculating the member resultant load. Then you let it equal to 0 at here. So in particular at here, so instead of a general P, so let's put a P naught at here. Okay, let's put a P naught, right? So P naught basically means if I solve for the P naught, and then we get Fi over that. So we get basically that's the amount of external force will ultimately result in joint separation, right? Joint separation here. Okay. So, of course, this is not the actual, right? This is not the actual external load at here. So you can use this P naught divided by the actual load P. Okay. So P at here is actual load, the actual external load. So you look at the difference between the current actual external load and the threshold external load. If it is still greater than 1, so you're safe, right? You're safe, okay? And if you're less than 1, then basically you get a joint separation, which is not safe. Okay? So in terms of joint, tension joint, bolted tension joint analysis, the requirement is here basically the 3 different type of calculations that are here. You got to basically look at the question, what type of a safety factor you are required to calculate, right? And then you calculate accordingly. Good. So that essentially wrap up all the knowledge that needed for the tension joint at here. Okay. And I'll make use of the rest of the time to go over an example at here. Okay. So any questions so far? Okay. So let's go over an example here. So this is a part of the problem number 4, assignment number 8. Okay. So I'll skip some details, right? But I'll go over pretty much the procedures for that question. Okay. So this is problem 4 in assignment 8. Okay. Okay, I'll take a picture into my note. Okay, so let me put down some descriptions for this question right here. Okay. So here's a number of given conditions. Basically, you're using the bolts and clamping this pressure vessel right here. The cylinder head is a steel, and the cylinder is a grade 30 cast iron. So there are two members right here. I think this question basically no washers. There's no washers. Okay, underneath the head or above the nut. Okay, there's no washer here. Okay. The thickness of the first member is D, and the thickness of the second member is E at here. Okay. So the D is equal to the same as E, which is 20 millimeter at here. And the bolts used in this application is a ISO 5.8 grade, and D is 12 millimeter coarse series. See, all of the keywords, actually you got to be careful when you see the keywords here, that when you look up the table, right, you got to look at the right place to find the right information. Okay, yeah. What else is here? So what else? Basically, there are a few more here. So it says the effective sealing diameter is 150 millimeter. Okay. And there is a static pressure 6 megapound. Okay, so internally there is basically the static pressure 6 megapound here. Okay. Okay, and then 10 bolts used at here. So there are 10 bolts surround the gasket. Okay. 10 bolts here, and you see this is basically actually a seal, right? Just a seal at here. Okay, so this should be enough. Oh, right, one more. We're talking about a non-permanent joint. Okay. The question asking you to calculate load factor NL and also separation factor. N. Okay, so two factors. Okay. Yeah. So when you see this kind of question, what should jump into mind shouldn't be the detail yet, because basically the bigger picture should jump into mind here is, first of all, you need to calculate the bolt stiffness, and second of all, you need to calculate the member stiffness, and then third of all, you can calculate the load factors or separation factors using appropriate formulas. Okay, so that's the sequence for this type of question right here. Okay, yeah. So the bolt stiffness and the member stiffness that we have gone through, so I probably skip some detail, and then you will do that in your assignments. Okay, and but I'll show you the bigger picture, how to finish this type of question in here. Okay. First of all, we actually what we need to do is, okay, so the solution in here is, okay, let's call P is the external load per bolt. Okay, so external load per bolt here. Okay. So let's see, how do we calculate this external load per bolt? Okay, because the question didn't give you that directly. So what question give you is, it give you an effective sealing diameter and a static pressure, and then 10 bolts at here, right? Yeah. So basically, we have a effective sealing diameter. So that effective sealing diameter will give us the area of sealing, right? So that's how much effective sealing area corresponding to that pressure, internal pressure. And this one can be calculated very easy, so let's call it A. So A equal to pi d squared over 4. I think I'll use a different d at here. Let's call it d naught here. Let's call this is d naught. Okay, because we have the measure diameter d for the bolt, right? Yeah. So this is a pi times 150 millimeter square over 4. Okay? Yeah. Let's keep it as it is. Okay, so you got a certain value millimeter square, right? Okay. So once you get this one here, and you have the total pressure 6 megapound, so the total pressure is 6 megapound, right? Then the total force, right? So the total force is equal to what? The P total times the area, right? So F total force divided by area give you the total pressure. So now total pressure times area give you the total force. And total is, I'll keep the megapound here. So this is where you got to be careful with the units here, right? Megapound unit is what? Yes. Yeah. Yeah. Megapound unit is millimeter square, right? Yeah. So we can keep this 6 at here, and then times the pi at here, 150, and divided by 4. Okay. So that'll give us the total number of total force at here. And what you do know is, if you keep this calculation, what will be the unit out of here? Meganewton? No, megapound is Newton per millimeter square, right? Millimeter square. So if I don't do anything at here, the results should be Newton, right? Should be Newton. Okay. So chances are it's probably too big, so you could times 10 to the power 3, and you get a kilonewton out of here. Okay. Yeah. So now once we find the total force, then the individual load on one bolt, right, is what? Is the total force divided by 10, and this gives us approximately 10.6 kilonewton. Okay. This is the one that you will actually use, right, for your safety analysis. Okay. Is that good? Yeah. So I'll get started like this. I'll skip some steps here. So as I said, the second step, let's call it step 1. The next step is to calculate the bolt stiffness. Okay. And this is where you need to look at the table, follow the procedures in table 8-7. Okay. I mentioned several times now. You've got to be very, very comfortable with using that table, okay? Otherwise, you're not get it right in the final exam. So this one here, you need to exercise, and I have the formula written actually previously, but okay. So if you calculate this one, you get 539 meganewton per meter. Okay? Yeah. the stiffness of the bolt is 539 meganewton per meter. So that's the part you're going to have to exercise yourself. And then member stiffness. So member stiffness here. So member stiffness for this portion, the typical process that you do is you're going to have to sketch out all the members, right? Sketch all the members clamped between the bolt and the nut. Okay. So in this particular case, as we said, how many members? There are only 2 members here, right? There's no washer, so you don't have to worry about it. But if the question specifically said there's a washer here or here, okay, then you have to find what? The washer's thickness first, right? In the previous lecture, I give you guys some handouts. There's a whole bunch of tables, and that you will have to use for finding the washer stiffness and sometimes also the height of the nut, right? Yeah. So in this case, it's actually not bad. All you need to do is sketch 2 members, and both members happen to have the same thickness. So first one is steel, second one is cast iron. Okay. Both have the same thickness of 20 millimeter. Right. That's basically the member that you're talking about here. And once you finish this sketch, to find the member stiffness, then you draw a symmetric conical pressure shape. Okay, symmetric. Yeah. So this sketch needs to be symmetric, but in this case, it just happened because the 2 members are the same thickness. So it's kind of aligning each other at here, right? Yeah. Once you sketch this properly, right? Sketch it properly basically means use the appropriate length. Then identify how many frustum are we talking about here. So in this case, how many frustum? 1, 2, right? Only 2, because they all have the same trapezoid shape, but they're different materials, right? Yeah, different materials. Okay. So then, to calculate each one of the stiffness, you can still sketch 1 frustum, just kind of enlarge it here. The top is D, and this is the thickness T, which is 20 millimeter, of course, right? Yeah. Okay, so what will be the capital D value? Let's see if anybody still remember that. What will be the capital D value? What's the top length? Basically, the capital D here refer to which portion? This portion, right? Yeah. It always starts with how much? Okay, so 1.5 D. Okay. Yeah. And the D at here is the major diameter of the bolt. So D here in this question equal to, how much is it again? So 12 millimeter. Okay. Yeah. Now basically sometimes if you recall that, what could be the other way I'm giving the information for 12 millimeter is what? M 12 times, for example, I don't know, 1, right? Okay? Yeah. So that's your capital D. This is your T here. Then you can use the formula that K equal to 0.577 times, what is it? 4, no. Pi ED long 1.155. Okay. You can use this formula to calculate the stiffness for this trapezoid here. Okay. And you also have to find out what is the basically the Young's modular for steel. What's the Young's modular for cast iron? Okay. This one you can find it from A-5, table A-5. So there's going to be a lot of table lookups, right? A lot of table lookups. Okay, sometimes I give you the results in the question. Okay, yeah, just to make your life easier. So find the E, and you can find the steel, and for the cast iron here is the same shape. So you ultimately have the same formula except the E at here, right? Except the E. Okay. So you'll find that the steel part is 4,470 meganewton per meter. The cast iron part has 2,160 meganewton per meter. Okay. So now you can calculate the total stiffness, which is 1 over K steel plus 1 over K cast iron. Okay. And then you get 1,456 meganewton per meter. Okay. So almost there. Okay. So now you get the member stiffness now. Let's call this member stiffness, and you got the bolt stiffness now. Okay. So let's calculate the load factor now. So let's call it step number 3. Okay. So load factor calculation is NL equal to SP times AT minus FI over C times P. Okay, C times P. So you need to calculate C first, which is KB over KB plus KM. Okay. So that gives us 0.27. And AT, okay, is the tensile stress area, right? Tensile stress area. So this one you need to look at the table 8-1, okay, table 8-1 to find the tensile stress area. So that gives us 84.3 millimeters square. Okay. And SP, okay, is the proof strength. So that comes from ISO 5.8 information. So grade 5.8. So this one you need a table 8-11. Okay. So you get SP equal to 380 megapound. Okay. So let's take a look at the table 8-11 at here. I think I have a table 8-11. Okay, so 5.8, you see that's 380 at here, right? 380. Okay, so 5.8. Okay. So all of these, once you have this, they're all good, and except FI here. FI, because it's non-permanent, so use a 0.75 times AT times SP. So that gives you 24 kilonewton. Okay, 24 kilonewton here. Again, there's a little bit of unit you need to be careful here. So AT is millimeter, and SP is meganewton. So times 10 to the power 3, you get kilonewton here. Okay. Yeah. And finally, plugging everything into this formula, and you get your NL, which is 2.89. Okay, so it's safe. It's a load factor, which is safe here. And then separation factor, last one, okay, is, let's call it N naught equal to Fi divided by P1 minus C. Okay, so which is 3.10, so which is also good. Okay. So that's kind of summarize this type of question, right? For bolted joints threaded with threaded fasteners. So my expectation has been very clear to you guys now. Okay, so what's needed, what's not, right? And make sure you practice and are comfortable with this. Okay. Any questions? All good? Okay. Thank you.